So then we get to the third category, which is analysis. Analysis, what I mean here is like you're given some equation. You're sort of like the convection correlations, except for these, this often just arises from geometry, not from like empirical observation. So geometrically, you can go through and like compute a lot of these. So you see lots of sines and tangents and things like that popping up. Where do you go to find these? So there's a couple places. This thermalradiation.net, this link here. This is a library that was put together by some faculty at University of Texas, Austin. If you want to see what the internet looked like in like 1989, go to that site, because I don't think it's been updated since then. But it's a really cool reference. Like you go through all these different scenarios, and what you'll pretty quickly realize is there's these buckets, these categories. Okay, it's a 1D problem, and I've got a curved surface and a flat target, and it's arranged in this way. Like there's a view factor for every one of those situations. Is it exhaustive? No, it's not, but there's a lot there. So that's one place that you can go. The other place you can go is EASE. So EASE has view factor libraries built in. I just pulled like 6 examples from the library. There's, I don't know, probably 70 or 80 that are in there. You can go through and you try to sort through, by type, by situation, curved surface or not. And some of these will have the explicit formulation here. So what you do is you just call that function, or if you want to just go view the code, you can like pull out the equation and use that. But yeah, I mean, you can see like the trickiness of this is just getting the definitions right. So computing the right angle or getting the right length or whatever it might be. Questions on the libraries? I think it's pretty straightforward to use once you understand what you're trying to do with it. So, okay. Good, then the last thing I'll talk about is, won't make y'all write this out, but something called Monte Carlo ray tracing. So if you're really interested in this, this is something I've actually done a lot in my own research. I do stuff with concentrating optics for solar energy, but one of the applications is, we need to figure out for these surfaces that reflect in a systematic way, they're not diffuse, how does light go from one surface to another? So there's no view factor that applies, right? It's not diffuse, it's what you call specular, it's directional reflection. So we use this a lot, right? And it's a very powerful tool. But the main idea is that you take a surface, let's say the surface at the bottom here, and you're trying to compute how much radiation leaving the surface down here hits this surface up here. So this example that's shown, there would be an analytical view factor for this, but let's assume there's not. So the idea is that you just sort of randomly pick some position on this source plate down here, just random number generator, randomly pick a position, and then you emit a ray. And that ray is chosen to emit in a random angle. So maybe that's over here, and then it's over here, and then it's over here. So you're combining the randomness of location with the randomness of emitting angle, and then you just trace that ray out as far as it goes and decide whether or not it actually intersected with that surface that you care about. So you do that millions or tens of millions of times until your answer stops changing, and you are left with what is the view factor. So ultimately, what you're trying to do is here, you compute the number of times you hit that surface divided by the number of times you tried, and that's your view factor. And that's a good intuitive understanding of what a view factor really is. So it's a really flexible method. Like I said, you can do it for non-diffuse surfaces. You can do it for like wavelength dependence, all this stuff that view factors don't really account for. Any questions on this? Okay, I guess that's it for today. So thank you.